All right, so chapter 19, it's about planar kinetics of a rigid body, impulse and momentum. And these are things that are not new to us. In chapter 15, we'd learn about linear and angular momentum and some conservation principles about the two. So for linear momentum, if we assume the rigid body made of as a collection of small particles, then the linear momentum of the entire body is the product between the mass of the body times the velocity vector of its center of mass. Okay, and so it will be a vector and has the magnitude of m times v and units kilogram meter per second or slug foot per second in the direction of the velocity vector of the center of mass. For angular momentum, we learn about the angular momentum of just one particle or a systems of particles, but here the systems of particle form of a body. And so considering the point P, the angular momentum of point P of one particle, this would be of mass, this is particle I and has the mass mi, although we can take it as dm, infinitesimally small mass. Then the angular momentum about P again would be the position vector r crossed with the linear momentum of the particle I, and then for the entire body would be a matter of integrating. We can explicit this further, so will be just for particle I as the it will be the angular acceleration of the omega times r squared. It's angular acceleration of that this product omega times r, yes, angular acceleration times the mass. And then we have these additional terms which appear to be linear momenta times distance, so linear momenta of about point P of the center of mass. So there's a rotational effect, and then there's the offset effect about point P. Now when we take the entire body and integrate over the body, and the mass of the particle becomes that infinitesimal dm, then the three integrals become one that includes the y of the centroid g of the body. X over square is the coordinate along the x-axis through P of the centroid, and then the third integral, it's an r squared times dm, and that's going to be the the mass moment of inertia of the body about point P. If point P coincides with the center of mass of the body, then we get this simplified form. So angular momentum about the centroid is going to be mass moment of inertia, centroidal mass moment of inertia times omega of the body. So this is also vector, has the direction of omega because Ig is just a constant specific to the body, although not as a rule. We can have systems in practice that their mass moment of inertia changes. We'll look at an example in just a little bit. Okay, so the earlier equation that when we looked at the mass moment of inertia about a point P other than the center of mass, can be in a process that is not much different from what we learn on energy conservation. So it can be written in a form like this one, where the mass moment of inertia, centroidal mass moment of inertia of the body times omega had to be augmented with these additional products. So it will be the centroidal coordinate y times linear momentum of g in the x direction, and centroidal x times the linear momentum of the center mass in the y direction. Okay, and then the earlier equations that were introduced are customized for the case where the body is performing either a rectilinear or curvilinear translation. So that means that there is no rotation, and we have so there's the velocity v, and every point has the same velocity. So linear momentum of the body will be the mass of the body times the velocity of center of mass, what could be the velocity of any point really. And then angular momentum is zero because about the center mass is zero because we don't have any rotation. Although if we take it, it's not discussed here, but if we take the angular momentum about a point other than the center mass, and the body performs a curvilinear translation, then these terms here are no longer zero. So angular momentum about a point other than the center mass in a curvilinear translation is not zero. But that the book does not go through this or does not emphasize this aspect. If we have rotation about a rigid body about a point O other than the center mass, then linear momentum is going to be, for a given instance, the velocity changes as a vector. So linear momentum is the mass of the body times the velocity of the center mass of the body, and angular momentum is going to be centroidal mass moment of inertia of the body times the centroidal mass moment of inertia. Sometimes it's useful to write the angular momentum as the product or about the axis of or the point of rotation. We're talking two-dimensional motion all the time. So it's going to be moment of inertia of the body about the axis of rotation times omega. So alternative to using the equation angular momentum about g, we use angular momentum about the axis of rotation. And in case of general planar motion, we have so this is a construction that shows the body that performs a combination, could be seen as a combination of rotation and translation. And the equations, the linear momentum equation is the same, unchanged, and then the angular momentum equation, the one that was derived earlier. Now we could instead use or evaluate angular momentum of the instant center of the body. So for that particular position, find the instant center, calculate the mass moment of inertia of the body about the instant center, and you crossed it with or rather multiplied with the omega vector, which has a k direction, and this gives us the angular momentum about the instant center. Okay, so these are the three general cases, and we're now going to discuss the principle, impulse, and momentum. So what happens when we have an external force or an external moment, how those can be captured in changes of the linear or angular momentum. So the principal linear momentum, linear impulse and momentum, is the same as for particles. So if we take the sum of forces, acting upon the particle, and evaluate these integrals between two instances of time, t1 and t2, then this is going to be the difference between the final at moment t2 linear momentum minus the linear momentum of the body t1. Okay, and the left-hand side is the impulse of the forces acting upon the system. Again, something that we saw early in chapter 15. Now, if we have a moment acting upon the body, so these forces were not necessarily pointing to, so they can have the effect of a rotational effect, that is a great moment or moments. So in that case, we can write that some of the moments about the centroid, it's going to be the time rate of change of the angular momentum. Okay, so same as we had it earlier, sum of forces is time rate of change of linear momentum. This is Newton's second law, and it's actually the way Newton's was formulated it originally in the 17th century. Then for moments, so the effect of the moment acting between t1 and t2, this is the angular impulse, is going to be the difference between angular momentum, and this is about the center of mass. So the impulse about the center of mass of the body, it's the difference between angular momentum at the lateral time minus angular momentum at the initial time. Okay. So, and we can of course write this equation for about the a point O, about which we axis of rotation, if we have a rotation about fixed axis, and it might be times more convenient to operate with it if we have a body that rotates about an axis other than the centroid. Okay. So these two equations are the principles of angular or impulse and momentum, one for linear impulse and momentum, and the other one for angular impulse and angular momentum. The two equations, which are vector equations, can be stated as in two dimensions as initial linear momentum of the body plus the impulse of the forces, sum of impulses of the force acting upon the body, equals its final linear momentum over the x-axis, and likewise for the y-axis. So linear momentum initially about the y-axis, sum of force in the y direction, equals linear momentum in along the y-axis at an instant 2. And then for moments, initial angular momentum of the center mass plus the impulse of the moment, this integral equals final angular momentum of the body. If we have systems of interconnecting bodies, although the chapter is called Planar Kinetics of a Rigid Body Impulse of Momentum, but if we have systems of bodies like a pulley and the rope, massless rope, and the weight attached. We can look at the combined system, pulley, rotating, and rope translating, and we can have the sum of linear momenta in the x direction, linear impulses in the x direction, final sum of linear momenta and for y direction, and for the rotational angular momentum impulses of moments, angular impulse that is, and final angular momentum. Okay, there are some sample problems and also problems for us to solve. Let's look at the conservation of that's page 540. Conservation of principle when it comes to angular momentum and linear momentum. So for linear momentum of a systems of particles, if the system is isolated, that is, there's just internal linear impulses which are in pair but opposing, so they don't have a net effect. Then we have the system linear momentum at instance 1 equals the sum the system linear momentum at instance 2, and these are the sum of vector sums of the linear momenta at time 1 and time 2. For angular momentum, we can write a similar type of equation. So evaluate I about the center mass with a fixed point. So we have the system's angular momentums, sum of angular momenta about O at instant 1 will be equal to sum of angular momenta at its system 2. So the total angular, either linear or angular momenta, can be conserved. You can have one. You can have conservation of the linear momenta about one axis, but not the other. If you have no force about one x-axis, for example, the linear momenta about x-axis is conserved. And then for when there's no external moment acting, the angular momentum it's conserved. Okay. There is a section on impact of rigid bodies. We're not going to discuss it. The chapter is about this that we just covered. There is a chapter review, page 556. So again, no impact, and I'm going to. There are some problems, not very many, where the mass moment of inertia of the system is changing. For example, here you have an athlete that it's spreading his arms together with some dumbbells, or a satellite deploying or retracting solar panels. So what I did, I prepared a working model, and it shows a system consisting of let me lower this. So consisting of a rod and two identical masses. And what I did, I removed gravity. So this happens in the horizontal plane. There is no gravity acting, and so we can look at angular momentum conservation for this model. All bodies with mass, they have an initial angular velocity of 20 radians per second. And then I have two actuators that do the same thing, and oscillate, change the length harmonically. And if I hit run, you'll see this accelerating or slowing down depending on the mass moment of inertia of the system. So if the two discs, which each have 50 kilograms, the rod is smaller mass. I can have it slightly bigger mass. Okay, so as the masses move away and towards the axis of rotation, which is here 0, 0, then the system's changes angular velocity, again without any external effect. Think of skaters spreading their arms to slow down and or bringing them close to their body to speed up, and other similar experiments that you can do. Maybe you're on an office chair and you can start a rotation and then spread your legs and then bring them closer to your body to see the effect. So let me hit run, and one is it shows the angular velocity of the system, and the other one shows the distance between the two yellow discs. Okay, so the effect is clear. So as the particle move closer to the axis of rotation, the mass moment inertia of the assembly rod and the two masses, it's minimum, and in the position where these are the farthest away, the total mass moment of inertia is the highest, and it's when the systems has minimum angular velocity. Okay, so this was it. I'm stopping here, and we'll do a couple of exercises in class. Okay, well, thank you for watching.